Hello everyone, welcome to another Lessons Learned video. Today we're going to discuss the stability of radicals in organic chemistry. So hopefully you're familiar with what a carbocation is. A carbocation essentially is a carbon that has that's got two things attached, really three, and then no lone pairs. For this reason, since it has three things attached, so in this case a hydrogen, two carbons, but it could be anything else, it's going to be sp2 hybridized. And let's explore what a carbanion is. A carbanion is similar, but the only difference is that we have a lone pair of electrons as opposed to an empty orbital like we do here. So we're going to have a net negative charge on this carbon. It's going to be sp3 hybridized as opposed to sp2. Now a radical is kind of in between. Instead of having no electrons or two electrons, we're going to have an unpaired electron, a single unpaired electron. That's going to be a radical. Now the radical is going to be somewhere in between being sp2 and sp3. It's not quite one or the other. We know that for carbocations, the stability pattern is going to be that basically if you have a primary carbocation, so if I have a primary carbocation, it's going to be very unstable. But if I have a secondary, well, this is a methyl carbocation, not a primary, but if I have a primary carbocation, it's also very unstable. But as we go into a secondary carbocation, it starts to get more stable. To have a tertiary, it's very stable. So the more substituted the carbon is, the more stable the carbocation is. Now, when it comes to carbanions, it's the opposite trend. So, for example, a tertiary carbanion is very unstable, but as we move toward having less substituted positions on that negatively charged carbon, we're going to get increased stability. I could do this as this color again, just because consistency. So a methyl carbanion is really stable. Now, what is the stability pattern of a radical? The radical is in between, but it's actually going to be a little bit more similar to a carbocation. Therefore, it's going to follow the carbocation trend. So if I have a methyl radical, my pen is not working, so hold on a minute. If I have a methyl radical, it's going to be less stable than a primary carbon radical, than a secondary carbon radical, and the most stable one would be a tertiary carbon radical. So the trend is like that of the carbocations. Now the resonance can also affect this. So if we have, for example, say we have a molecule that looks like this. We have a molecule molecule that looks like this. Which one would be the more stable radical? They say it's going to be the molecule on the left side. And the reason is that it's going to be stabilized by resonance. So the way the resonance works on this is that you can have these arrows. So this single electron can represent it as moving here. So the outcome will be that we'll form a pi bond here, and then there's going to be a single lone electron on that carbon. So there's going to be a resonance between these two structures. The molecule is going to be somewhere in between these two structures. It's not going to be at one or the other at any point. So that means that the radical is going to be spread out over two carbons. This carbon and this carbon. That's more stable than it being stuck on a single carbon. So therefore this is more stable in this case. The radical could also be benzylic. So if we have a ring that looks like this, let's say I have a tertiary carbon there with a radical on it. And we compare that to a similar molecule, but where the ring is not a benzene ring. Right? Which one is going to be more stable? So, I mean, it's pretty straightforward. It's going to be, this one is going to be more stable due to resonance with this benzene ring. So what can occur is that we can have a single electron here, one of the pi electrons here, and one of them here. So the resonance form will look like this. And the pi bond will be among these two carbons. Then there's going to be a single lone pair on this carbon. And this can occur again, so you can see that this can occur between this pi bond and the lone pair again, and then half the electrons here are going to go here. And this radical is going to move across the entire ring until it gets back to the other side. So it's spread out among a lot of carbons, so it's a lot more stable than it again being stuck on this carbon, even though this is relatively more stable compared to a methyl or a primary or secondary radical, but it's not stabilized by resonance like this molecule.